Okay, Assalamu alaikum everybody. طلاب صف الرابع. I'm happy to do this session with you. I'm hoping everyone is interested and everyone is going to be with us for the whole semester. Now, as you can see, our subject is Catalyst Science and Technology. We're doing this course only for this semesters, and I'm hoping to do material science for the next semester. Before we go through deeply in catalyst, we need to know something about chemical kinetics, rate of reaction. What we mean by rate of reaction, of course, we mean the speed of any reaction. Rate is a speed anyway. But in chemical kinetic, we use the word rate instead of speed. Using the word speed is not wrong. So why we studying chemical kinetics before we go to the catalyst? Because chemical kinetics, in other words, the rate of reaction, which we study now, is affected by using a catalyst. In general, as you know from your previous studies, that a catalyst can enhance these the speed of reaction. That's why we use a catalyst in the industry. So chemical kinetics is the study of discussion of chemical reactions and discussion, sorry, of chemical reactions with respect to reaction rates or effect of various variables, temperature, such as stirring, such as light or catalyst or whatever. So there are many topics to be discussed, and each of these topics is a tool for the study of chemical reaction. Now, the study of motion is called kinetics. So kinetics, we're studying the movement, the motion of particles, and how this motion can be affected by using, for example, different temperature, or can be affected by using catalyst. So the study of chemical kinetic, therefore, includes the rate of a chemical reaction, and also look at this chemical reaction, of course, and the factors that influence or alter or control the rate of reaction. All these words are same, influence or alter or control, all having similar meaning in this term. Right. So in chemical kinetics, we study how molecules react, how they are react, and why they are react, and bond breaking and new bond formation. Of course, in a chemical reaction, what is happening? There is two processes happens in any chemical reaction. It's like bonds first breaking and then a new bond formation. So a chemical reaction is like a rearrangement of the atoms, how they are combined to each other. There is no nuclear change. There is no identity in the atom. The only thing happening in chemical reaction is recombination again, is rearrangement of the atoms in different pattern. So at the microscopic level, we are interested in amounts reacted, formed, and the rate of their formation. At molecular or microscopic level, the following consideration must also be made in the discussion of chemical reaction mechanism. What we mean by chemical reaction mechanism, we mean how that chemical reaction happening, what's the steps to make that product. Of course, different chemical reactions in general they have different mechanisms. The molecules or atoms of reactant must colloid. Look at this word, this is important, colloid. So we need a collision. We need a collision between atoms or molecules. We have a molecule A react with molecule B. We need them to have a collision between molecule A and molecule B. If there is no collision, of course, there would be no reaction. So molecules or atoms of reactants must colloid with each other in chemical reactions. That's first thing. And then it doesn't mean any collision means the reaction would happen. It's not necessarily, but we need first stable collision. The molecules must have sufficient energy. Concentrate on this word. So we need sufficient energy, enough energy. That collision would be with enough energy. Right. So the third thing, which is important as well, is the orientation. So we have three things should be exist all together for any chemical reaction to happen between A and B. One is the collision, two, enough energy, sufficient energy, and then the orientation. The orientation means how they colloid with each other, in what angle, on what side. Okay, so reaction rates, how fast the concentration of a reactant or product change with time. That's reaction rate. That's the definition of reaction rate. We can study the reaction rate either by measuring the change in concentration of a reactant, or we can measure the change in concentration of a product and how this change happening within a certain time. And why we saying time? Because we're saying rate. As far as we're saying rate, so rate means speed. Speed means you should have a time to measure. As you're measuring the speed of a car, when you say the speed of a car is 60 kilometers per hour, you mean within 1 hour it makes 60 kilometers. So you need time. In any speed or rate or velocity, we have time. So in chemical reaction, we don't have, of course, kilometer or miles. We have a change in concentration divided by time. Right. So the relation between the rate of a reaction and the concentrations of reactants is expressed by its rate law. So we have something called rate law. Let's take a simple example. We have nitrogen pentoxide, dinitrogen pentoxide, decomposed to nitrogen dioxide and oxygen. Very simple reaction. We have a compound decomposed to one compound and one element. Okay. Of course, all these are gases. For this reaction, we notice that the rate is directly proportional, ناسب طردي, directly proportional to the concentration of dinitrogen peroxide. It means higher concentration of dinitrogen pentoxide, it means higher rate of the decomposition. So there's a relationship between the concentration N2O5 and the rate of decomposition. We can put that mathematically to say rate equal K, that's a constant. As you know, in mathematics, when you have direct proportionality, you can equalize that proportionality by adding a factor, constant factor, which is called usually K, in this case, constant. And of course, K is equal rate divided by concentration. Remember this symbol, this one, this type of a bracket, this one. Notice that we use this in chemistry as a concentration. As a concentration. We mean a concentration. Usually that concentration is mole per decimeter cube. Mole per decimeter cube. So we have to be careful. There is another constant in chemical reaction. It's called equilibrium constant. It's called equilibrium constant, but that's different from this K. So be very careful about confusing equilibrium constant expression with those for rate laws. The expression for K equilibrium can always be written by inspecting the reaction equation. You need the reaction equation. And it contains term of each component. What we mean by this, we mean, for example, if you take the same example, this one again, so the equilibrium, all right, if you can't remember what we mean by equilibrium, I just give you a very short idea about it. Equilibrium, when we say the reaction is at equilibrium, we mean the rate for the forward reaction is equal to the rate of backward reaction. That reaction is reversible reaction. It means it has forward direction and backward direction. In other words, at equilibrium, the concentration of the reactants and the products are constant. There is no change in concentration. That's called equilibrium. I don't want to go through equilibrium because that's not our interest for time being, but we need to know just for about K, there is another K, it's called equilibrium constant. And it's different than the rate constant. For example, in this one, look at this one, K equilibrium equal concentration of NO2 to power 4, because the component here is 4, that's 4, times O2 divided by N2O5. It means the product over the reactant, and each concentration is raised to the power of the how many mole, that one. We have 2, we have 4, we have 1. So it's different from the rate. Right. So in contrast, in the opposite way, the expression for rate generally bears no necessary relation to the reaction equation. We don't need the reaction equation. The only thing we need is the reactant, and in general is raised to a power, again, the exponent, but sometimes is not. It depends on the order of the reaction. I don't want, again, in this case, to go through deep about order of reactions. In general, that's not our interest. Just want to go to the catalyst, but we need this general information about chemical reactions and about kinetics. Since the rate of a reaction has the dimensions of concentration divided by time, remember this, that's general, since the rate of reaction as the dimensions of concentration divided by time. The dimensions of the rate constant K will depend on the exponents of the concentration terms in the rate law. It means the concentration raised to what power? So K is different for different orders of reaction. K is different, has different units for different orders of reaction. We have zero order reaction, we have first order reaction, we have second order reaction, and probably we have third order reaction. Chemical reaction rates are the rates of changing concentration or amount of either reactants or products over time. I think we said that before, but we just repeat it for more concentration or change in amount. The units can be 1 of mole per second could be. We can use this, how many moles for each second. But it carefully to these units, you find out always there's a time. But something changed with time. Could be concentration, could be mass, gram, or ounce, kilogram, whatever. For change in concentration, the units can be 1 of mole per decimeter cube. That's change in concentration. And that's the rate. Don't confuse. Okay? Change in concentration can be mole per decimeter cube. Second, again, this one, we can say again, it's for rate. This is the change in the amount or concentration, again per time. Okay, let me say this again. I feel confusing now. In this one, what we're saying change in amount. How many mole per second, or how many kilogram per day, or how many gram per second. In this one, we're taking the concentration per time. And if you look at it, mole per decimeter cube, that's a concentration. And for each second. So we have like 2 units combined in 1 unit. One is for concentration, and the other one is for time. Again, in this one, gram per decimeter cube, because in concentration, we need to have a volume. Decimeter cube is used to be called liter. We don't use liter anymore. It is not AUPAC system. AUPAC system in chemistry is decimeter cube, which is 1,000 cubic centimeter. 1,000 cubic centimeter. Right, so with respect to reaction rates, we may deal with average rates. We have 3 types of rates. One is called the average rate, and one is called instantaneous rate, any at that time, certain time, or initial rate. Initial rate, يعني الابتدائي, when it starts. So the speed of reaction is called the rate of reaction. The speed of different chemical reactions varies hugely. Different reactions having different rate. Of course, some of them very fast reaction, like explosion, happens within very short time, or could be very short time, precipitation of insoluble salts from their ions in solution. It takes some time. Takes a little longer. Rusting, corrosion of nail left in the open air. مسمار بتترك مسمار في مكان رطب، تلاحظ أنه يصدأ. Takes rust. In other words, corroded. Takes too long time, very long time, formation of stalactites and stalagmites. I don't know if you have any idea about stalactites or stalagmites. Anyway, your aging is very long time. When you're growing up, again, it's a change. It's changing happening in your body, but it takes very long time. Okay, so in general, we plot concentration. That's a concentration, and that's time, and we measure that concentration change within time, either for reactant or product. Sometimes you can do it easy with reactant, or sometimes you can do it with product. Product, it doesn't matter. So this is a reaction. We have A change to B. If you look at carefully, notice that the curve is opposite each other. And with the product, the concentration is goes up by the time. With reactant, it goes down by the time because reactants is used up, so the concentration goes down. With product, it goes up because that's forming by the time. So usually, in general, how we study the change, how we study the rate of reaction could be volume of gas is given off. What volume of gas, for example, if we have carbon dioxide forming, we can measure the change in volume, or we can study change in mass, the mass of reactant, or the temperature change, could be the temperature change, or it could be the color, change in the color, because the change in the color comes from the change in the concentration of the reactant or product, or a precipitate form, acid, or change in pH, or change in conductivity التوصيلية الكهربائية. Could be different, be any one of these can be used for measuring the change. In other words, measuring the rates. So how can rate of reaction be measured? Measuring the rate of a reaction means measuring the change in the amount in of a reactant or amount of product with respect to time. Again, we're saying that concentrate on this. So we need to measure something change, as we said, like concentration, volume, mass, pH, temperature, color. But in general, we take the rate of a reaction by measuring the change in concentration, or sometimes the change in number of moles. So what can be measured to calculate the rate of reaction between magnesium and hydrochloric acid? This is another simple example. As you know from your previous study in chemistry, in general, metals with acids react with acids to give salt of that metal. In this case, because we're having hydrochloric acid, so we get magnesium chloride and is giving off hydrogen gas. And of course, magnesium is not very reactive metal, such as sodium or potassium, is less reactive, but still it gives hydrogen gas and magnesium chloride in this case. So how we measure the rate of reaction of this one? Okay. Either the amount of hydrochloric acid used up, because that would be used up as a reactant. So we can measure how many cubic centimeter, for example, per each minute that's change. Or we count the amount of magnesium chloride produced, how many grams for each minute, or the amount of hydrogen product, this one. So we have different one to tracing the rate of the reaction, either through the HCl change or magnesium chloride change or hydrogen gas change. Right. As we said, we have three types of rate. One is called average, one is called instantaneous, and one is called initial reaction rate. We go through each one briefly. So average rate of reaction, often denoted by delta concentration, divided by delta T, time. So the average rate of reaction is an average rate. It's not the rate at certain moment, giving you the average rate for the whole time, starting from zero time until the reaction finish, until the reaction complete. We take that time and we take how much change happened, excuse me, in change or product, and we divided that change in concentration by the whole time. So that's called average. I think it's obvious from the name what we mean by average. So the average rate of reaction is an average rate obtained by taking the change in concentration over a time period, all time, starting from beginning until the reaction is stopped or completed. For example, zero point 0.3 molar, that's molar, per 15 minutes. If that reaction finished within 15 minutes and the change of concentration is zero point 0.3 molar, so we divide that change in concentration. Remember, this M capital means molar, means molar. All right. Okay, sorry. So that's the meaning of molar. Okay. Now, average rate, again, rate of a chemical reaction computed as the ratio of a measure change, a ratio, it's a ratio, is a division of a concentration, a change in concentration by time, measure change in amount of concentration of substance to time interval over which the change occurred. That change in concentration you're measuring happened within what time? What time? So you divided that concentration by that time. So you get average rate. It's similar to this one in math. You have like delta y, if you consider this a concentration, and you have delta x, if you consider this the time. So you take that change in concentration, delta y, divided by that change in time for that change in concentration. So you divide 3 by 4 to get, it's like the slope, to get the change in y within time. what change of y happening within time. Okay, I think this is clear for you. So as we say, the average rate is something like slope. Again, concentration, that's time. That's for reactant. As we said, it goes down. And that's for product, it goes up. So what you're doing, you're taking this change in concentration divided by this change in time. That's the change in time, something in this case, for example, something about 500 seconds. In this case, you're having something about, I don't know, something 1.6, something about 1.6, let's say something like that. So 1.6 divided by 500. Of course, this is molar concentration, and this is second. That would give you, so delta C, that's C, divided by delta T, that's T. So you're dividing concentration by time, you get the rate for the reaction. This one, again, is similar. Similar, it's not different from this one, but this is for reactant, but this one is for the product. Remember always the opposite. And what we mean by the instantaneous rate of a reaction denoted as dC over dt, d differential c over d differential t at a certain time. This one is for instantaneous. For example, you want to measure this one here at this time. For example, let's say you want to measure the speed or the rate of the reaction at second 40 at this time. We draw a tangent to that point like that. That's a tangent. And you can take any change in volume or concentration divided by any change in time. All must give the same result because the slope is same for this line anytime, anywhere. If you take, for example, here, like that, example, this change with this change, again, you get the same result. I think you know that from mathematics. That's instantaneous, can be obtained from the experimental data by first graphing the concentration of a system as a function of time. We should do that first experimentally. Then finding the slope of the tangent. Remember this, slope of the tangent. Slope of the tangent. So slope of the tangent line at a specific point, which corresponds to a time of interest. What does it mean? It means at what time you want to measure the instantaneous rate. So you draw that tangent at that point, at that point. So the slope of the tangent line, you need to find out the slope, where at a specific point, which corresponds to a time of interest. Okay? For example, want it at this point, of course, the slope for the line will be different. So it means that slope for that line is different from point to point. Different from point to point because the speed or the rate change within time. It goes up first quickly and then gradually it's slowing down until that reaction stops. Right. So alternatively, experiments can measure the change in concentration over a very small time period, two or more times to get an average rate close to that of the instantaneous rate. The reaction rate for that time is determined from the slope of the tangent line. You can do like 2 points, very close to that point, and you can take the tangent, and again, you can find out the instantaneous rate. So instantaneous rate of a chemical reaction, rate of a chemical reaction at any instant in time, determined by the slope, remember the slope of line tangential to a graph of concentration as a function of time. So we determine the instantaneous rate at time t by calculating the negative of the slope of the curve of concentration of a reactant versus time, or by calculating the slope of the curve of concentration of a product versus time. Again, same. If you're taking product or reactant. Lastly, we have the initial rate. Initial rate of a reaction is the instantaneous rate at the start of the reaction. That means when T is equal 0. At T0, what is the rate of that reaction? Initial rate is equal to the negative of the slope of the curve of reactant concentration versus time at T0. Again, it's similar. Of course, initial rate is like a special case of instantaneous rate. Initial rate is a special case of instantaneous rate. It means it is instantaneous rate, but at t equals 0, not any time. Okay, we stop here, relative rates of reaction, and we do this in the second session. And thank you very much for your listening. I don't want to make the video too long for you. I do this as a second session.